Okay, good afternoon, everybody. I hope everyone's having a wonderful day. So before anything, I just want to mention that I'll be putting out the final assignment later today. It won't be that long of an assignment, but it will get you thinking. So it'll only have a few problems on it, but they require some thought, careful thought. So that being said, I want to get on to what I want to really focus on today. And I'm going to be showing you a concept that's, I would argue, is one of the most, if you were to walk out of this class and you're saying, okay, I learned about this thing called undecidability. I learned that there's languages that there's no algorithm that can decide them. There's all these concepts I've learned, at least depending on how you want to talk about them in terms of Turing machines, or you want to talk about them more in our discussion of what an algorithm is. This is one of the concepts that if you walk out of this class, whether you're an undergrad, a grad, or you're not really interested in theory, or you really like theory, this is one of those concepts that you will find helpful when describing and studying problems. It's the concept of a reduction. So this is going to be something that we're going to use a lot after this stage. So today I'm going to be focusing on this concept of a reduction and showing you how we can use it to show other problems are undecidable too. So whenever it is convenient, I'll use the word problem instead of language, but do keep in mind, remember, problem, language, tomato, tomato. That's the thing you need to keep in mind. They have a natural correspondence in the way we talk about them. So I need to talk about what a reduction is. So a reduction is simply an algorithm. So you could think of this is a Turing machine. I'll describe more formally what I mean by this in a moment. That converts the instance or input from pi1. So I have two problems, pi1 and pi2. So it converts the instances of pi1 to instances that are descriptions for pi2. So you might ask, Dan, what does that even mean? So you got to think of this not as an algorithm that solves a problem. It is actually one that's going to help us convert instances of one problem into an instance of some instance of the other problem. So, and the whole idea is that when I do this conversion process, that the instance I get has the same answer. So there's some wiggle around what same answer means, but I'll give you the traditional way that same answer means same answer. So if I were to describe that there's such an algorithm like this, so I'm going to give you a picture of what I mean by this shortly. It means that pi1 reduces to pi2, or sometimes we say pi2 reduces from pi1. So the fancy way of writing this down oftentimes is they use this less than or equals notation with an M. This means many one reduction or mapping reduction. So you might ask, Dan, what do you mean by mapping and what is a reduction? So for example, here are all of the valid instances of pi1. I've represented this as a set of all the inputs for pi1. And suppose it's really about deciding if something's in pi1. And the answers either are yes, the input is in pi1, or no, it is not. Note that if we're talking about so-called recursively enumerable problems, it's very possible that you can have inputs sitting out here. And those ones mostly just mean nothing for us if we're talking about decidability. However, I will be coming back to recursively enumerable languages in a little bit. So here's the idea. I want to be able to have this reduction so that if I were to take any one instance which falls into one of these two buckets, either the yes instances, meaning that yes, that input belongs to this language, or no, it does not belong to this language. What I would like the reduction to do is map it, as in convert it to an instance of pi2, which may be some of the instances in pi2. It may not necessarily be any one matching instance in pi2, but it'll convert it to some instance of pi2, either a yes in here. So if there's a yes instance here, it'll match as a yes instance here. That's what I mean by same answer. And a no instance here, it must be converted into an instance for which there's going to be a natural correspondence for those that are no instances here. You're going to see throughout this lecture what I mean by this. So this is the conventional way of talking about a reduction. And the whole idea here is that I have some way of describing one problem in terms of another problem through this reduction. So one standard view of this, and this is really the way I like to think about it, is that this gives you a bridge to talk about one problem in relation to another problem. So if you want to talk about, say, pi 1, and there's a reduction that gets you to pi 2, they might be able to say things about pi 2 if it relates to pi 1 in this way. I'll be talking about that shortly. So first, does everybody get the general ideas? I'm going to have some algorithm. It's going to convert instances of pi 1 to some instance of pi 2. And this algorithm's job, that's only the job of this algorithm. And what we would like this reduction to have, a very special property, is that it has to have the same answer. So when I say same answer, there's some fudging around we're allowed to do, but generally there's a natural correspondence between the two instances that I have, the original one and the converted one. But the point is that there's this reduction. Okay. So I'm going to show you, I'm going to get a little bit more formal about this, but believe it or not, it's actually not that much formal than this. Because the concept of a reduction is quite natural, if you think about it. The way I like to think about a reduction, if ever I'm not sure about, like, okay, what exactly that means, is I like to think about this reduction as some mechanism that allows me to use another problem to help me solve another problem. That's the way I like to think about it from the direction that we're going to mostly focus this on. There's a couple of ways you can interpret a reduction, and they both have their own worth or value. So I must stress that the thing I'm showing you here gives you a natural bridge, just like when I talk about, and say if I was talking about something like complexity theory, which I'll talk about later on in this course. In this context, this gives me a way I can go from one problem and talk about it in terms of a different problem. And if there's properties that different problems have, I can inherit those properties, which is what the power of a reduction really is, at least in one direction, or there's another way of thinking about it from another direction, which I'll get into in a moment. So what is a reduction? A reduction is just going to be a Turing machine that takes an instance of pi 1 written on its tape, and it's going to halt with an instance of pi 2 on the tape. So you might ask, okay, well, what does that even mean? So here's a picture to really help kind of cement this idea for you. So suppose that this is an algorithm for pi 1. So this is problem pi 1. And now I must stress that it's important to get the direction of the reductions correct. It's very easy, and heck, it even happens to me sometimes, where you get the reduction backwards. So just please keep in mind this picture when we're working through these things. So I'm gonna show you how I can design an algorithm for pi 1. Here's the idea. Let me just make myself a little bit more room in between here. So my algorithm, of course, takes an input W. So remember, this algorithm is just, we're going to think about them typically within the context of deciders. So it takes an input W. And what's going to happen is this input W is going to actually be given to my reduction. So I'm going to call that F. And what, as I suggest up here, is it'll take W, that's the input, and it's going to perform this reduction, which is this process. And that means it's going to leave on the tape when it's done F of W, which F of W is the converted instance, so that it's an instance of pi 2. And then if I have an algorithm or Turing machine, or in our case, a decider. That's really what we're going to be interested in. So whenever I say algorithm, I'm usually referring to a decider, as we've kind of established earlier. So here's an algorithm for pi2. And if it's a decider, then it must be able to tell me yes or no, or accept or reject, depending on what context we want to talk about this within. Sometimes the yes means something else than just a yes. It could mean that, like, you flip the logic and it's actually reject means yes, or and so on. But this will be generally the picture that you want to look at. Now, a question for you. What is a reduction in terms of Turing machines? What kind of Turing machine is the reduction based on the description I just gave you here? What kind of Turing machine would you like to think about this like? So remember, we've talked about a few different kinds of Turing machines. I'll give you a hint. It starts with a T. It's a transducer. Very good, very good. So it takes the input, it makes this transformation, it leaves this on the tape as input for this guy right here to do its work. Exactly. Perfect. So this should give you a general idea of how we can use the reduction. Is this clear, everybody? So this reduction's job is to convert the instances from pi1 to pi2 so that I can use some algorithm, in our case that means a decider, for pi2, and it'll be able to tell me yes or no answers. But the point here is that these yes and no answers, they match the ones that you would anticipate for this big box overall, which is the algorithm for pi1. So keep in mind that there might be output that comes out of this one, and then we could do some logic to that. For example, flipping the logic where like accept is a reject or reject is an accept. That's why I say yes, no on the outside of the box as opposed to inside the box. But we actually did something kind of like this the other day. Do you remember that? I kind of showed you this meta picture of a Turing machine, and I had them running in parallel, and then I said, okay, if it accepts for this one, do this. If it rejects for this one, do that. It's very much the same kind of setup I'm using here, except I'm trying to describe to an overall algorithm. Okay? So if you look at this picture carefully, it has very interesting consequences from a decidability and undecidability standpoint. So the first thing I should point out is pi2 must be at least as hard to solve as pi1. Why? Because every instance of pi1 can be converted to some instance pi2. So I already see that. So I can take any one instance of pi1, I can use this reduction to get an instance of pi2. But I want you to remember this picture I drew over here. Let me just move back over here. I'll come right back over there. I want you to look back at my picture over here for the reduction. So I want you to look at this picture and you can see what I mean by at least. So this is the picture I want you to keep in mind when I say this. So remember, I take every instance of pi1 and I convert each one to some instance of pi2. But notice that I don't necessarily guarantee that it captures every instance of pi2. Sometimes it will be the case that there actually is an equivalency between two problems, meaning that whenever I give you any one instance here, it actually corresponds to another instance over here, meaning that the two in fact there is an equivalency between the two problems. So generally there's some relationship they may have. For example, one may be the complement of the other, for example. But Does everybody see what I mean by at least as hard? So if I take any one instance of this and I can tell you it could be some instances in this, say the circle here, or some in here. Notice it isn't necessarily all of the instances of pi 2. So one way that I must stress that this is not necessarily a technical way of describing it is that I like to think of pi 2 like a generalization of pi 1. Just it's written in a different language, a different way of describing it. So in this context, you can sort of see pi 1 as a special case of pi 2 just described in a different way. And the means for which you translate it is using a reduction. Is that clear, everybody? So that's one of the major reasons why we might use one of these reductions. So note, I haven't said anything really about how hard. It's just that we know that it's at least as hard. So this also, if you look at this picture carefully, this also has some other strange consequences that are logical. So if we can solve pi 2, as in there exists an algorithm that solves pi 2, just to be clear, I'll mention this. There is an algorithm that solves pi 2. Then we can use the reduction to solve any instance of pi 1. So I have a question for you. What does that mean if I tell you that pi 2 is decidable? If I was talking about pi 1 and pi 2, what does this mean if I tell you that pi 2 is decidable? What's the relationship pi 2 has with pi 1? Yes, it's also decidable. Exactly. So that's the big thing you should take from this picture, because I've literally given you a cookbook for how to, if I know that pi 2, if I could solve pi 2, if I could give you some reduction that takes pi 1 and converts it to pi 2, and it gives me an answer, then most certainly I have a way to say, hey, look, there's an answer for pi 1 too. I just used the reduction. So this is the first thing I really want to point out. That is, if pi 2 is decidable, then pi 1 is decidable. Now I must stress, like I said, the direction of my reasoning matters a lot here. A common pitfall that students make, colleagues of mine make sometimes, even I make, is getting the reduction backwards. So remember, when I'm performing a reduction for pi 1 to pi 2, what I'm really trying to do is I'm trying to show you that there's some algorithm for pi 1 using pi 2. So just keep in mind the reasoning, because it's very easy to mix them up, because I'm going to tell you another consequence of this picture. So this is the one that we're going to mostly focus on. And this is the one that's going to be the most useful for us when we talk about undecidability. So I want you to keep that picture in the back of your mind. It'll very often be useful when we start getting to proving some claims. In fact, I would even encourage you, if you find yourself just not sure what to do, try drawing one of those pictures and try to fill in the blanks and see, okay, is this a reduction? I lost my turtle friend. There we go. I rescued the turtle. Okay. So let's talk about this. So here's an important consequence that you need to be aware of. This is the one that we're going to find most important for us, at least with respect to undecidability. So given problems or languages, however you would like to speak about them, problems or languages pi 1 and pi 2. And if there's this reduction, pi 1 reduces to pi 2, then there's this very interesting but important detail. So keep in mind the following. Whenever pi 1 is undecidable, pi 2 must also be undecidable. In the notes, I'll include a sketch of how you would prove this fact, but it boils down to that picture over there. What you do is you take the assumption by contradiction. So what you do is you would presume that there exists a decider for this guy, for pi 2. And then what you do is you build, your goal is to figure out a decider for pi 1. So what you do is you construct a reduction that takes you from pi 1 to pi 2. Then what you do is you go, okay, well, I could describe an entire algorithm for you that correctly will decide pi 1. But here's the way you get the contradiction. It's very simple. You already know pi 1 is undecidable. So it's undecidable, but also decidable. That's how you get the contradiction. So that's going to be generally the sketch of the proof that we will use today. But is the reasoning clear for everybody? So in one direction, if I want to know, okay, is this problem decidable or not, I can go from pi 2 and say things about pi 1. But if I want to talk about something being at least as hard, like I said initially, if I know that pi 1 is already undecidable, then most certainly it must be that pi 2 is also at least undecidable. So it's the same idea. So this idea generally applies as well when you talk about whether languages are not recursively enumerable as well. So you can do things even worse than this. Also, if pi 1 is not recursively enumerable, and pi 1, there's a reduction from pi 1 to pi 2, or pi 1 reduces to pi 2, then pi 2 is not recursively enumerable. I lost my little penguin. Oops. The penguin didn't like this fact, by the way. So this is actually by the very same reasoning I just described before. Everything I just said about undecidable, replace it with not recursively enumerable. And you would have the exact same setup. So have I convinced everybody of both of these facts, just to be clear? So if we're all good with this, I'm going to proceed. So if we're all good with this, I'm going to describe one other concept that we're going to use very often. For those that may be reading the Sipser book, you might appreciate what I'm going to do next. Or have read the Sipser book. For the sake of simplicity, because I think at this stage, we understand how you encode a Turing machine, right? And we also know, okay, if I have a Turing machine, I have some input, or even say if I gave you multiple Turing machines, you would know how to describe those in binary, right? So I'm going to just use some special notation to make this a little easier for us to describe the problems we're going to consider. For the sake of simplicity, we will denote with these angle brackets, A1, A2, all the way up to AN. Close the angle brackets. Notation to represent. I lose my little turtle friend. Maybe the turtle liked the way I described these things before. To represent the encoding of objects A1, A2, all the way up to AN together. So just to be clear, just as to give you an example, what I mean by this, if I were to describe to you with the angle brackets M and W like this, this is the encoding of Turing machine M and input W, such as with the universal Turing machine. Remember when I was talking about the universal language and I had like some Turing machine and some input W? So this would be how I would describe this to you using these angle brackets. Let me make that one a little bit more pointy. There we go. It wasn't pointy enough, okay? So are we okay with this notation? So I'm going to frequently use this notation to make things a little easier for us to describe the languages we're going to consider. So if it helps at all, I'm going to describe for you the universal language in the context of this notation. So if I give you the universal language, it means I'm giving you some Turing machine, some input W, such that W is in fact in the language of the machine. M is a Turing machine, and W is in the language of that machine. So this would be another way you could describe the universal language from the other day. So are we okay with this notation? Just want to be clear with everybody. We'll find as we're going further up, you're going to feel like very much the last bit of this class is going to be where I'm going to start stacking abstractions on top of each other until the point where, say for example, if you're in 411, you'll feel very much like by the end of this class, like you got back to 340. So, so hopefully, so if you're taking 340, you'll feel very much like right at home by the end of this class. Okay, so if we're okay with this, I'm going to start off with using my first reduction. Last day I talked about the halting problem briefly at the end of class. I'm going to show you a way I can use reductions to show that the halting problem is undecidable. So I described in a different way using an equivalent model of a Turing machine, and you formulate it quite similar to the universal language. So it's quite natural for me to use the universal language for my reduction if I'm going to describe the Turing machines the way I like to. So what we're going to do is I'm going to prove the next theorem for you. So this is our first example. So remember, when I'm doing these reductions, I'm going to be basically building up a collection of problems that I know are undecidable, so that if I were to consider a new problem, I may have another tool in my toolkit to throw at it and say, hey, look, that problem's undecidable. If I find just some reduction, then most certainly that new problem that I've considered, if there exists a reduction and the original problem's undecidable, then most certainly the new one I'm considering also must be undecidable. So that's going to be the tool that we're going to use. That's what we're going to use these reductions for. The halting problem. The halting problem. And I'm going to call this L of H. LH. LH. Actually, I'll say specifically it's LH, not L of H, because that sounds like it's a function. It's a language. LH is undecidable. Is undecidable, where I'm going to define LH as follows. So the language, sorry, I just about did it myself. LH, let me just switch my marker here. Let's try this marker. So if I want to describe the halting problem, I can describe it like this. This is much better. So suppose I give you pairs the encoding of a machine and its input such that M halts on input W. That's what the halting problem is within the context of what we're looking at. Is that there's some Turing machine, and then there's some input. So in fact, if I wanted to be a bit more precise, I can say there is M is a Turing machine, and M halts on input W. Anyways, so has everybody got the idea of what the halting problem is with our new notation? So what I'm going to do now is I'm going to use what I drew over here to help us just to get a general sketch of what we're going to do. I usually recommend doing something like this offhand. Sometimes it gets a little helpful. So I'll first kind of draw you how I'm going to tweak around with this, and then I'm going to write out how I'm actually going to do it. So I'm just going to give you the general idea, and then I'm going to proceed. So what I would like to do, as I said earlier, is I would like to make it so that I have a reduction. So I'm going to show that there's a reduction. So that the universal language reduces to my halting problem. Some people call it the halting language. So if you look back at my picture over here, pi 1 is LU, universal language, and pi 2 is our halting problem. So everywhere where you see pi 1, you just simply put the universal language. Wherever you see pi 2, we're going to put our halting problem here. So based on this picture, let's think about it. So LU, remember the universal language, it takes as input an encoding, which is a machine and some input, right? As encoded as we've seen before. What we would like it to do is produce a reduction, this reduction F, because of the fact that the input for the halting problem, what is the input for the halting problem again? Can somebody tell me? What is going to be what I'm going to consider as what's on the tape for the halting problem? What's it encoding? Don't be shy. Don't be shy. So so I know that I'm getting for the universal language, I'm getting a machine and some input. I use this reduction. What should be on the tape when I'm done this? Yeah, so what is it though? Like what should be fed to the algorithm for the halting problem? So what's the input for this? Yeah, it's just, yeah, exactly. It's just the machine and the string. So it has its own that you're going to build. So you're going to have, so I'll call them M prime and W prime. And that's what's going to be given to this algorithm. And in the context of us just being very clear, remember, every time I say algorithm, I'm referring to a decider. So just remember that. So based on what I said earlier, for the sake of argument, what I'm going to do is I'm going to presume that there's a decider for the halting problem. And then what I do is I effectively build this. So my job is really to first describe this to you and then summarize what this box does. And if I could do that and show that there's a direct relationship between LU and LH as required by a reduction, we're done. Because if I showed you that this box actually exists, then most certainly we get a contradiction, because I already know that there is no algorithm for LU, right? So just, if you're not sure about this, convince yourself that this box that I just drew here can't actually exist. So what I'm doing is I'm asserting that, oh yeah, we'll assume that there is one, and then I basically show you that if I assume that the halting problem has an algorithm that solves it, then most certainly I can design one such algorithm for the universal language. So is the game plan clear to everybody? So give me 2 thumbs up if we're all good with this. Okay, so let me proceed. So just whenever you're not sure about kind of the setup for this, just remind yourself of these boxes. And I must stress that some of the reductions will be more complicated, and they will not just be looking like this. It may be the case that you may have multiple boxes, or you may have a chain of boxes. So just be aware that when you have a reduction, you may actually have a whole chain of reductions. Or you may have it where the reduction converts and creates one Turing machine, and then it uses a different Turing machine. But I'm going to try to keep it roughly into this format as much as I can to keep things straightforward. Because it's usually that's usually what we would like. So let me write out first the setup for the proof, and then I'm going to describe this reduction for you. And then remember, from more of an algorithm's perspective, the reduction is going to be, in fact, an algorithm, but in the context of a Turing machine, I'm actually going to be describing the Turing machine to you in the reduction. So what the algorithm is going to be doing is it's essentially going to be where I'm going to describe the Turing machine that your algorithm is going to use. So that box, I'm going to describe the Turing machine that's going to go in that box with F. Okay? So here we go. So just keep that in mind. It's very tempting to be like, yeah, no, it literally runs it. It's like, no, it builds. You have to convince yourself that I'm describing to you a Turing machine that is going to then put onto the tape that output that I've just described initially before. Remember, F of W. Yes. Yes, it's many one. Yeah, it's many one. So all I need to care about is that for every instance or input for my language of question, so in this case, I care about the universal language. I'm going to take each one of those and I'm going to translate each one of those into one for the halting problem. Now, remember, like I've said, the reduction could obviously produce complete garbage if it doesn't actually sit in the language. So that's something just to keep in mind as more of a technical note. But we only care about decidability here. So hopefully my point is clear about that. There's going to always be these yes instances and no instances that we care about. Okay, so assume there is a Turing machine, H, that decides the halting problem language, whatever you'd like to call it, LH. And we do this for the sake of contradiction. It'll matter later. I just like the setup that I'm doing a contradiction proof straight up for you. That's usually why I do it this way. So I must stress that whenever I'm talking about a reduction, I'm usually going to omit the phrase many one. And sometimes I may even just simply not write the M. That should be the subscript off to the side of the inequality. Sometimes I just will straight up will write an inequality. So whenever you do see that, just assume I'm talking about a many one reduction unless otherwise stated. Later on, we're going to see different kinds of reductions. For example, they may have a P instead of an M. So just be aware that there's going to be other kinds of reductions that are going to specialize on top of this. So first, let us present a reduction so that I get LU reduces to LH. So I'm going to describe now the reduction, and then once I have that description, you can think of this like a subroutine that my algorithm is going to use. So just keep in mind that I'm describing this subroutine. So I'm going to be describing it just like if I were to have some parameters it might use, and then when I actually run the algorithm, it's going to take advantage of this fact. Sometimes it really does matter that I say this. So let reduction F, so it's going to take, it takes the encoding of MW, and it, as output, it's going to give me M prime W prime. So this is going to be our goal here. So that M accepts W if and only if M prime halts on W prime. So remember, we want them so they have the same answer. So we want M to accept on W, and if that happens, that's a yes answer, right? And then if M prime halts on W, that's a yes answer. Does everybody see that? So sometimes when I'm doing these reductions, it's not going to be really clear at first when I'm like, oh, I draw this connection. Then really, in reality, I've described some way of connecting the instances on one side or the other. But the point is that they purely capture yes and no instances on the other side. But for us, I'm just going to try keeping things simple at this stage and just say yes, yes, which is what we normally like. That's typically how we like to define these kind of reductions. So anyway, so here we go. In the reduction, so just to reiterate what I meant by that is that if, say, for example, I say something, say it rejects on one of these, then the other one accepts, there are analogous ways of describing the yes and no's. That's why I said earlier that a yes might mean something different than an accept. At least from the context of the Turing machines. You'll see what I mean when we get there. This one, it's nice and straightforward. So in the reduction, we're going to let W prime equal W. Makes sense, right? I'm not going to touch the input at all for my machine. So I'm going to leave W prime alone. It's just going to be W. But I'm going to do the following. Then the description. So when I describe this Turing machine to you, you can think of it like a conversion or construction. Hopefully I didn't get cut off entirely. So it's going to be some description of a Turing machine. So what you need to convince yourself of is that I have some Turing machine that can make these modifications, okay? So then the Turing machine, so of M prime, so now I have to tell you what M prime is the following. So I'm going to describe it in high-level description for you. And my goal, of course, is to convince you that all of these are valid things to do with a Turing machine. So the first thing, I'm going to say that M prime it simulates M on its input. Now remember, I said that the inputs are the exact same amongst the two, so we're okay with terms of this. So this isn't anything too strange. It's just like what we talked about with the universal Turing machine, right? So it's just gonna do that. So we haven't changed anything about what the Turing machine does. Remember, I'm describing the Turing machine to you. So now this is where I'm gonna make some changes. So first part, not so much. If M accepts, then M prime halts and accepts. And that's what you would expect, right? If the original machine accepts, then it most certainly halts, right? Now, what we would like it to do, so this is what you need to keep in mind when I'm doing these kind of reductions. I would like to create something that when I feed it to the halting problem, my algorithm for the halting problem, I want it so it looks like something that should reject for the halting problem. So does anybody have any ideas of what I should do with this machine if it rejects? So if M rejects, what should I do? Any ideas? And remember, all you need to know is that as long as I can describe this to make the modifications to the Turing machine, we're okay. So if it rejects, what should we do? So remember, we want to give this machine over to my algorithm for the halting problem. And remember, I'm assuming it actually works. Yes. Yeah. So you're going to take the idea that you said. So I'm going to take it one step above this. So what you're going to do is if M rejects. So remember, you got to keep in mind that I want to have it so that this M prime W prime, it goes off to the algorithm for the halting problem. And I want to make sure it accepts for that decider, for LH, which means that it has to halt. However, if it rejects, then most certainly it has to be that it never halts, right? So if this rejects, then most certainly what I would like it to do is I would like it to do something else that's much more interesting. And I'll briefly describe how I would actually do this. That M prime goes into an infinite loop. So if you are able to determine that M rejects, now keep in mind, this is about the description of the Turing machine. If it accepts, remember the definition of our acceptance for our Turing machine is simply that we are in the accepting state, right? So we don't have to do anything here. All of these, how did I define rejection for our Turing machine? Anybody have any ideas? Do you recall? So I remember how I defined the transitions. So there's kind of two parts to this. So I'll tell you the first one. The first one is just simply that it's not in an accepting state. What's the other one? Yeah, well, that's basically what you do. So that's actually what we're going to make M prime do. So if we have it where, say M rejects, that means that there wasn't a transition defined. So if there wasn't one, it halts immediately. So what we do, this is the fun of this. So what I'm going to do is I'm going to define a new state for all of my transitions where they're undefined to go to this new state and then have it for every tape symbol. it's just going to keep looping at this new state that I'm just going to create. So it will never actually ever halt. It will never, because there's always going to be a way that when it reads the tape, it's just going to simply just stay in that state that isn't a final one. And it's defined on all the tape symbols. So that's actually how you can construct this modification. Okay, so now I've described the reduction to you. So this will give me something I could feed over to my algorithm, my decider that decides LH. So here's how the algorithm's going to play out. So here we go. So given input MW, below describes. So once we finish this, we'll stop for today. Below describes an algorithm, and I'll call it U, just in the sake of that it's essentially going to be a universal Turing machine that decides LU. So here's the steps. So here's the steps for this. Here are the steps. Okay, so here are the steps, and it's really quite simple. It's just basically that box I just described to you earlier. So you build. So you take in MW for my reduction, and it gives me on the tape this encoding of a Turing machine M prime with input W prime. And now what you're going to do is you're going to run H, which is my decider for the halting problem. So I'm going to run H with input M prime W prime. So now here's the fun question. What should I do with the outcome of this? Because remember, H is a decider, so you know it's always going to halt. It's going to say accept or reject. What should this decider say? Somebody tell me. So if H accepts, what should happen? So if H accepts, and then I'll say and if H rejects, what should I write in those two blanks? So remember back to the connection I'm trying to draw between these two Turing machines. So if H accepts, remember, this means that when I feed that M prime to H, if it accepts, it halts, right? By definition. So you most certainly want to make sure it accepts. And you know that this M prime, it loops forever. Remember? So you know that it most certainly should reject. So just to summarize this last bit, just to be clear, observe that M accepts U if and only if M prime halts on W prime, which equals W. However, since U decides LU, we arrive at a contradiction. For some reason I wrote at twice. At a contradiction as the universal language is undecidable. This would, of course, imply that LH is also undecidable. And we're done. So that being said, I'm going to stop right here. I apologize for taking a little bit more time than I was hoping, but it's sort of the fun when you ask questions of everybody. I think it's a really important concept, that it's important that we kind of do this together. So anyways, when I come back, we'll do more reductions. And that being said, I want to say thank you very much and have yourself a beautiful day. I'll see you later.